Hello and welcome. Differentiation under the integral sign. Today we're going to be looking at the integral from 0 to infinity of the arctan of 8x minus the arctan of 2x, the whole thing over x. So we're going to, let's actually call this I. That's the integral in question. And we're going to introduce a parameter. Pardon me. We normally been using k's and t's so far, so let's be a little bit different today and use lambda. The question is now where we're going to introduce the parameter. Good candidate, the 8 or the 2. Does it really matter? The answer is doesn't. In my book, Differentiation under the integral sign, which is under the tab Advanced in my website, I've done it both ways. Today, or for the purpose of this video, I'm going to call the 8 lambda. So this is going to be 0 to infinity, and we're going to have the arctan of lambda x minus the arctan of 2x, the whole thing over x dx. And now we're going to differentiate both sides of this equation with respect to the parameter lambda. So we're going to have di by the lambda is equal to d by the lambda of the integral. I'm going to leave a bit of space because I'm going to just save myself a line. I'm not going to just rewrite it on the next line. I'm just going to move that inside the integral in a second. So that's arctan of 2x over x dx. And then, of course, by Leibniz integral rule, we've got constant limits here. We can swap differentiation and integration, but when we go inside, because we've got two variables, we should really write it as a partial. So d by the lambda of this, so this is going inside, so we no longer need it here, is equal to that. So we're going to now carry out the differentiation. Di by the lambda is equal to, notice that if we split the fraction here, so we got this term here and this term here, there's no lambda in here, so this will disappear completely on differentiation. So that's going to give us, I'm carrying out this differentiation now. First of all, by the chain rule, we're going to get, when we differentiate with respect to lambda, an x, which is the whole point of all of this, of course, because it's going to cancel this x which is there. This is the x at the bottom. And then the differential of the arctan of lambda x is going to be 1 over 1 plus lambda squared x squared, and it still needs to be integrated with respect to x. The x, of course, will cancel, and we got so far di by the lambda is equal to this quantity here. This is an arctan, just needs a little bit of tidy to get into the standard form. So we're going to factorize the 1 over lambda squared outside the integral. So this is now 1 over lambda squared, 0 to infinity, and this now is going to be x squared plus 1 over lambda squared, which I'm going to write it like this, dx. And now I'm going to carry out the integration. Still di by the lambda is equal to the 1 over lambda squared. Now this is a standard arctan integral. So this will integrate to 1 over this quantity here. So 1 over lambda is going to be just lambda. And then we're going to have the arctan of x over 1 over lambda, so we can call it lambda x. And we need limits there. I'm going to put them here, 0 to infinity. We're going to have 1 over lambda. That's from this bit here. And the arctan of infinity is pi over 2. The arctan of 0 is 0. So this is in fact equal to pi over 2 lambda. So now we need to, let's not forget, this is that di by the lambda. So what we're going to do next is we're going to integrate both sides of this equation. So if di by d lambda is pi over 2 lambda, our I of lambda, this is just the log, is going to be pi over 2, the log of lambda plus a constant. So in other words, I of lambda, so let's write it in its full glory. I of lambda is this integral here. Let's write it, arctan of lambda x minus the arctan of 2x, the whole thing over x, dx is equal to pi over 2 log lambda plus a constant. So we need to, pardon me, again, I need to evaluate this constant c. So I need to pick a suitable value for my lambda in order to evaluate my c. And the sensible thing to do is to say, you know what, let's, in order to create a zero integrand, very easily, if we call it lambda is equal to 2, this will just give us 0 here. So the left-hand side will produce 0 is equal to, what do we have now on the right-hand side? We've got pi over 2 log 2 plus a constant. So our constant c is going to be negative pi over 2 log 2. And therefore, we have just found that our integral not to infinity of the arctan of lambda x minus the arctan of 2x over x is going to be equal to pi over 2, the log of lambda, and the constant is this quantity here. Therefore, in order to find the required integral, if lambda turns out to be 8, our integral not to infinity, the required integral now, arctan of 8x minus the arctan of 2x, the whole thing over x, is going to give us pi over 2 log 8 minus pi over 2 log 2, which c will simplify to pi over 2 log 4, which we can do even better than that. And we can just say, because of course 4 is 2 squared, move to the front, pi log 2. A highly enjoyable integral, a little bit different to what we've done in recent videos. I think that's about it. Nice and to the point. I hope you found it useful, and I hope you're getting better now at this particular technique. And for the time being, I will be signing out. See you very, very soon.